The simulation on the relationships between applied force, displacement, and equilibrium is an interactive educational tool designed to help students understand the fundamental principles of Hooke's law and the behavior of springs in various configurations. This simulation allows students to investigate how the applied force, and effective spring constant change when two springs are connected in series or parallel. Additionally, it enables students to explore how the applied force, displacement, and spring constant affect the potential energy stored in the spring. By providing a visual and hands-on approach, the simulation enhances students' understanding of these crucial concepts in physics. The simulation focuses on the principles of Hooke's law, which states that the force exerted by a spring is directly proportional to its displacement from its equilibrium position. The simulation allows students to explore how these relationships change when two springs are connected in series or parallel, and how these changes affect the potential energy stored in the springs. Students can adjust the applied force to observe its effect on the spring system. The applied force causes the springs to stretch or compress, leading to a displacement from the equilibrium position. The spring force is the restoring force exerted by the spring in response to the displacement. The simulation allows students to observe how the spring force changes with displacement and the configuration of the springs. The displacement is the distance the spring is stretched or compressed from its equilibrium position. Students can observe how the displacement changes with the applied force and the configuration of the springs. The spring constant, K, is a measure of the stiffness of the spring. The simulation allows students to adjust the spring constant and observe its effect on the spring force and displacement. The simulation allows students to connect two springs in series or parallel and observe how the effective spring constant changes. Furthermore, the simulation allows students to observe how the potential energy changes with the applied force, displacement, and spring constant. The simulation provides a hands-on approach to exploring the relationships between applied force, displacement, and equilibrium. By adjusting the applied force, spring constant, and the configuration of the springs, students can observe the following key concepts. When the applied force is increased, the springs stretch or compress, leading to a greater displacement. The spring force increases in response to the displacement, following Hooke's law. The spring constant affects the stiffness of the spring. A higher spring constant results in a stiffer spring, which requires a greater applied force to achieve the same displacement. Conversely, a lower spring constant results in a more flexible spring, which requires a smaller applied force to achieve the same displacement. When two springs are connected in series, the effective spring constant is lower than the individual spring constants. This means that the combined spring system is more flexible and a smaller applied force is required to achieve the same displacement. When two springs are connected in parallel, the effective spring constant is higher than the individual spring constants. This means that the combined spring system is stiffer and a greater applied force is required to achieve the same displacement. The potential energy stored in the spring increases with the square of the displacement. A greater displacement results in more potential energy stored in the spring. The spring constant also affects the potential energy, with a higher spring constant resulting in more potential energy stored for the same displacement. The simulation on the relationships between applied force, displacement, and equilibrium offers several educational benefits. 1. The simulation provides an interactive and engaging way to learn about the principles of Hooke's law and the behavior of springs. Students can actively participate in the learning process by adjusting the applied force, spring constant, and the configuration of the springs, and observing the effects on the spring force, displacement, and potential energy. 2. The concepts of spring force, displacement, and potential energy can be abstract and difficult to understand. The simulation provides a visual and tangible representation of these concepts, making them more accessible and understandable. 3. Students can experiment with different applied forces, spring constants, and configurations of the springs, and observe the resulting changes in the spring force, displacement, and potential energy. This exploratory approach encourages critical thinking and problem-solving skills. The simulation provides a practical application of the principles of Hooke's law, which are fundamental to many real world phenomena, such as the design of mechanical systems, the behavior of materials, and the storage of energy. This helps students see the relevance of these concepts in everyday life. 5. The simulation introduces students to the process of data collection and analysis. By observing the changes in the spring force, displacement, and potential energy, students can collect data and analyze the relationship between the applied force, spring constant, and the configuration of the springs. To implement the simulation in the classroom, teachers can follow these steps. 1. Begin with a brief introduction to the concept of Hooke's law and the behavior of springs. Provide examples to illustrate these concepts and explain how the simulation will help students understand them. 2. Demonstrate the simulation to the class, showing how to adjust the applied force, spring constant, and the configuration of the springs, and observe the changes in the spring force, displacement, and potential energy. Explain the importance of observing these changes and how they relate to the principles of Hooke's law. 3. Allow students to explore the simulation in small groups or individually. Encourage them to experiment with different applied forces, spring constants, and configurations of the springs and record their observations. Provide worksheets or prompts to guide their exploration and data collection. 4. After collecting data, have students analyze the relationship between the applied force, spring constant, and the configuration of the springs. They can use the formula for Hooke's law and the equations for the effective spring constant in series and parallel configurations to interpret the data and draw conclusions. 5. Facilitate a class discussion to share and compare findings. Encourage students to reflect on what they have learned about the relationships between applied force, spring force, displacement, and equilibrium. Ask them to consider how these concepts apply to other areas of physics and everyday life. The simulation on the relationships between applied force, spring force, displacement, and equilibrium is a valuable educational tool that brings the principles of Hooke's law to life through an interactive and engaging context. By allowing students to investigate how the applied force, spring force, and effective spring constant change when two springs are connected in series or parallel, and how these changes affect the potential energy stored in the spring, the simulation provides a hands-on learning experience that enhances understanding of these fundamental concepts. This interactive approach not only makes learning more enjoyable, but also fosters critical thinking, problem-solving skills, and a deeper appreciation for the relevance of these principles in the real world.